I'm Matt Godbolt.
And I'm Ben Rady.
And this is Two's Complement, a programming podcast. Hey Ben.
Hey Matt.
One of these days we're going to have to come up with a different intro to this podcast. So I'd be like, good afternoon, Benjamin.
Hello, Mr. Godbolt.
There we are. That's better. Little variety there for our listener.
Yeah.
What are we talking about today?
Today I want to talk about an idea that entered my brain a few weeks ago at work, talking to one of our colleagues. He had asked me a question about this, and it was one of those times where it's like, I'm now going to reflect on what I have done for almost my entire career and realize something that I have been doing this whole time that I never actually put into words until just now when you asked me a question about this.
Isn't mentoring such a rewarding experience?
Yes. Being forced to use the talky bits of your brain, which normally lie dormant in the process of programming. And it
so
turns
true.
out there's a whole extra CPU over there that you can use for thinking that you just normally don't, right? It's like a graphics card in your brain.
Right.
That you can do all kinds of interesting things with.
So what did he ask for?
Yeah. So we were talking about automated tests, of course, because what the hell else do I talk about? And he was saying, like, how do you write automated tests for when you're doing performance optimization? Like, do you write a unit test that shows that the performance is bad and then go and improve the performance and then you see your test pass? And I say, no, I don't really do that. I kind of treat performance optimization like refactoring. And he got this look on his face like, wait, what?
Oh.
And I had never really thought about it until that moment. But yes, there is actually, I think, a whole category of things that you can write automated tests for, perhaps. I think it's difficult to write good tests for them, but you can, and so I sometimes do. But for the most part, there is a category of things of which performance optimization is one, where my explicit intention is to keep the sort of observable behavior, and I can define what that means very specifically later, but keep the observable behavior constant while changing the code in some other dimension. And obviously, like, the most common thing that you do with this is to change the design of the software so that it's easier to understand or easier to change.
That's the very traditional refactoring definition.
Yeah, that's like the real, changing the structure of code without changing its behavior as defined by a set of automated tests, right, is like on line 7 of Martin Fowler's refactoring book. And I know that because I've said it so many damn times. Of course, it's probably not on page 7, and I've just been wrong this whole time. But the general reason why one might want to change the structure of code without changing its behavior as specified by a set of tests is for the purposes of reducing complexity or making the code generally easier to change or easier to understand or removing duplication, things like that, which actually are all kind of complexity. But another reason that you might want to do this is performance optimization.
Right.
And I really do view it as something that is, for some definition of behavior, almost, but not quite, orthogonal to behavior. And I think a great example of this, I was recalling an earlier podcast where we were talking about comments and documentation.
Yep.
And you were saying how you have had many situations, and I have also had this. I have had the same experience where you're changing code and you're adding comments to it because the reason that you're changing the code is very not obvious.
Right.
And you want to leave some hint to the later reader, who may be you, as to why this code that looks so complicated and weird has to be this way.
Right.
Right? And in those moments, quite often what I am doing is I have my unit tests that are running that are telling me that I haven't changed the behavior of the software.
Yes.
I have a separate thing, which might be like a flame graph or some other sort of tool that's telling me, okay, is the performance of this code that I'm changing, what is it? Is it getting better? Is it getting worse? And I'm changing the code trying to optimize that performance metric while making sure that the sort of observable behavior
Right.
I haven't broken anything or introduced any bugs as a result of doing that. And I realized in that moment, answering this question for this person, that it's like, oh no, that is just purely refactoring. It's not like refactoring. It is refactoring.
It is refactoring, except the dimension that you're measuring is not complexity or ease of change, like you said, although they can be flip sides. It is the performance of the code. Now, splitting hairs here, and you did leave enough wiggle room to have this definition there as well. Obviously, how fast something goes is an observable property of that system. You can measure how long it takes to do something. And but for the vast majority of tests, like vanishingly rarely do you care to the level to write tests that say, I have a part of my specification is that I must be able to process this thing in under some amount of time, right? That is possible. You do sometimes get that. It is part of the specification sometimes, but very, very often it's just like as fast as you can go, and we'll let you know if it's not fast enough kind of feel, right? So one tends not to do this. No, tends not to write automated tests, but you could. So yeah, absolutely, this is refactoring. And you mentioned other dimensions. So like I have just spent the entire day moving code around, not because it makes it less complicated, although it does. That's not my reasoning behind this, but it's to change the compile time of my code and the sensitivity to change for my code, which is C++, and at the moment therefore means, if there's loads of stuff that's uninteresting to most people in header files, then every time I make a change to something that is an internal part of my algorithm, anyone who's including my header has to rebuild, and I don't like that. I don't like to expose it, so they shouldn't be able to observe that in the first place. It's one of those rare things that C++ is weird about, is that like the physical layout of my code is actually part of my, not really API, but it's part of the problems that I give to my my users, part of the sort of sensitivity to change. And so I'm refactoring, and it is refactoring, to take stuff out of header files and hide them away from people. And they should not be able to observe that, other than hopefully their compile times go down, or when I make a change, they don't have to compile half their program. So yeah, I totally get it. And performance is another one of those.
Yeah, absolutely. Absolutely. Now, I will say, again, here comes all the asterisks and caveats to this bold statement that I make at the head of the thing, because the real world is a little messy. There are many situations in which the way that you achieve a performance optimization is by changing the behavior.
Yes.
Right? The actual observable by unit test behavior, right? Like, oh, we're going to just, filter out some things from this collection before we process it, for example, would be an example of how you would speed something up.
Or an API changes so that, hey, if I hand you each individual event one by one, it's a lot slower than me giving you, here's just a big old chunk of events, off you go. And then we lose, that kind of feel to it, which is like, well, batching or otherwise changes the API. You could probably write an adapter to make the test still fit that hole, but you have still changed the way things look.
Yeah, absolutely. So I'm not trying to say here that all performance optimization is refactoring, because there's many types of performance optimization where you do actually change the behavior on purpose in order to make things faster, right?
Yes.
But there is definitely a category of performance optimization where it's like, I've got this function, I know what my inputs are, and I know what my outputs are, and the question is, how quickly can I do this? And I do all kinds of crazy little things in that code to make it go faster, and the observable inputs and the observable outputs are not going to change at all. And the only thing that changes is like, the time, or maybe like the clock cycles that it takes to execute that code. And I think that's part of the reason why I tend not to write tests for these kinds of things, because those tests are very expensive to make reliable. Right?
For
if
certain.
You're going to write automated tests for performance, you need to have control over your hardware. You need to have control over your execution environment. You need to know what architecture you're running. There's all these variables that you need to control in order to write. It's very easy to write unreliable tests for this, right?
You
just say, start time equals blah, end time equals blah, if total time less than whatever, right? You can make unreliable tests for this very easily. But if you want to make reliable performance tests, they're very expensive to get right. They're very difficult to design testable. It's very difficult to design code that is both performant and designed to be tested in that way.
Correct.
And you want to save that effort for basically like the hot loop of your program, right? The thing that really makes all the difference, right? Or maybe you have a few hot loops, but you want to save that because they're real expensive. So most of the time, if I've just got sort of a general performance or throughput problem of some kind, I want to have some other tool that is telling me what the performance is, that is measuring it in some other way, using like application level metrics or tracing or some profiling tool, or there's a million. That's probably a whole episode of itself.
I mean, we've done some observability. We've talked about observability before. It's another dimension of observability. Is like how many things am I processing per second? What's the average latencies of X, Y, and Z? And you can look at them. And to your point about like not writing tests for this, what I tend to do is I do spend a bit of time to have an environment where I can, at like 2 a.m. when I know no one else is kind of on the network, on one of our machines that otherwise is dedicated to running daily jobs for the trading day, in my case, I copy code over to it and I run it, and then I don't assert anything about it. I just record it. And then I can graph it over time. And then that gives me the sort of observability and dimensionality of like a repeatable benchmark rather than just the day-to-day watching of Grafana and seeing things change around or whatever. Maybe it's just a busy day today, or maybe it's a quiet day. Why are my metrics thing? But I then have a time series where I can look back over something. And it doesn't matter that occasionally it does blip up if, for example, I don't get the isolation exactly right. I'm not going to get a false positive or test failure, false negative test failure here. But what I can do is see trends really, really easily. And I can say, what on earth happened 3 weeks ago? What commit came in and suddenly made everything just a little bit worse? And that's really valuable. So, but anyway, that's orthogonal to the idea that the changes themselves, especially when you're in a sort of the loop of like making those modifications, those optimizations, that is a refactoring operation where you're like, hey, I wonder if we should use shell sort rather than insertion sort in my sort method, that nobody exogenously can see what kind of sort I'm doing, because as long as the numbers come out in the right order, nobody cares.
Right. Yeah, and the tests are there in that case only to make sure that if you like accidentally switch from like a stable sort to an unstable sort, that doesn't matter.
Yes.
Right? And that sort of gets at the heart of like, what it means to have changing code where the behavior doesn't matter as verified by a set of tests. Like the behavior that matters and the behavior that doesn't matter is specified by the tests. And that's one of the reasons why it's important not to overspecify behavior in your tests, because not only does it make it harder to refactor, but if performance optimization in this way is also refactoring, it makes it harder to optimize your performance.
Right.
Because you're asserting behavior that you don't actually care about.
That stable sort versus unstable sort is a perfect example of something that's so easy to write a test that will fail for the wrong reasons, right? If you accidentally assert stability of order, so like just for those who aren't familiar,
I guess we should define what stable and unstable sorts are. Maybe.
Exactly. So like when you're sorting things, you sort by a key, and that may be only one of the properties of the objects that you have in an array or container. What do you do when there's a tie? One thing is like, it doesn't matter. Everything that has the same priority or whatever the key is, doesn't matter which sequence they appear in. They all have the same values to you that you're interested in, or it doesn't matter. Whereas, and so an unstable sort, which is often more optimized, when you're doing the sort, it doesn't matter if you have two things that are the same. If you end up switching them or not switching them, doesn't matter, right? And that's great, and that's often what you want. Certainly if you're writing the sort. But sometimes, if there's a tie, you still want to keep them in the same sequence. That is, objects that have the same value need to be kept in the same sequence as they were originally. So, maybe that's, Anyway, so that is much harder to achieve in a sort algorithm and more expensive. And it could be so easy to write a test where you have things that do have the same values in them, and then you assert them to be exactly some output form. And that exact output form is stable. And then later on you change your sort and they get switched around and you're like, why is my test failing?
Yeah, right. Exactly.
And people, we do this with like things like sets. If you things that return sets of objects, sometimes you forget that maybe that set is not ordered or not ordered, and then again changing the internals to make the set deterministically ordered or not could be an optimization. It's like, hey, I don't have to keep them in sorted order as long as it's still a set of all the things that you said in any order. That's fine. Overspecifying is bad. Anyway, I think that's...
No, that's exactly right. And switching, for example, from a list to a set in order to achieve some performance optimization, and having a test fail because the test cared about the order, but really you don't actually care about the order, you just care that it's a collection, is a perfect example of this, right? And so that's one of the many reasons why overspecifying in tests and not being very intentional about what it is that you assert and what it is that you don't assert can make your test less useful, because it doesn't let you do this. Another area that I think is that is like this is thread safety.
Oh, wow.
I have never found a way to write. Well, that's not true. There's a few very limited situations in which I've been able to do this, but it is very rare that I can get confidence that multi-threaded code works as I intend it through automated unit tests.
Right.
You can sometimes do things that will allow you to disprove that confidence with like fuzz testing and some kind of like performance testing where you're just putting it under lots of load, and then you get some error that you don't expect or some state that you don't expect, and you're like, well, clearly I screwed this up. But just because it works doesn't really tell you much of anything.
No,
you might have just got lucky, right?
Exactly right.
So thread safety is one of those things that sort of unfortunately, I have said this thing before where it's like, I don't really think of myself as a great programmer. I'm just a good programmer with great habits. Thread safety is one of those things where it's like, well, I hope you're the best programmer that you can be today because you just got to get this right.
Yes. Yeah.
And so it comes down to really just reading through the code and understanding the synchronization primitives and the way that you're using the threads and just making sure that you get it right. And hopefully, as you're doing that, you can use your test to make sure that while you spent 100% of your brain power on this very tricky problem, you didn't also have an off by one error, right?
Yes. Yeah, it reduces the dimensionality of the kind of failures you're going to get. But as you say, that I'm sure we've all written the sort of small loop of like, let's make 10 threads, hammer it for 1,000 times and just assert that everything seems to make sense afterwards. And then you write that test, and that test is, if it passes, well, all you've done is shown that one roll of the dice didn't come up with an obvious flaw. Now, there is one exception to that particular approach, as in like, let me clarify that. That is kind of a useful tool to just prove that there isn't an egregious issue straight up, but it's maybe not something you'd even want to check in because if there is a problem, you're just going to have a flaky test. Now, it doesn't mean to say that, that's not valuable in some way, because if it's flaky, maybe you have got a bug in there. But if you can have automated thread checking, and some of the systems these days will allow you to do like thread sanitizing checking, where the code is instrumented and every read and write to memory is checked to be sequenced with other threads' reads and writes. There is some potential that having a test that exercises the behavior you want, this threading behavior, might, even if it doesn't actually happen in that particular test pass, if the thread checker is on, it might go, wait a second, although it didn't bite you this time, this thread wrote to this memory location and another thread read from it, and there was no synchronization between those two, so good luck. That might be valid, but that actually is, you mentioned fuzzing. Fuzzing is another place where having in combination with the kind of checking that you can do with thread sanitizers, also things like address sanitizers and memory sanitizers and things like that do these checks, it becomes part of an approach to finding those issues. But again, these aren't really tests in the same way that you and I think of tests. So to your original point, you lean on the tests for the correctness part, and then you think really, really, really hard about the threading part. And if you think hard enough, usually you can design a threading out of it, which then means that you don't have to worry about it at all.
Yes, exactly. Think really hard about it, and then go explain it to someone else on your team.
And if they still think it's a good idea.
Yeah, right. A, to use that sidecar GPU to think about it again, and
Yes.
also to make sure that they agree that we're not about to introduce a foot gun into the system and break a whole bunch of things.
For real. Yeah, it's interesting. Yeah, it's interesting how much, on my team even recently I've been discussing about the introduction or otherwise of threading, and opinions diverge as to how much trouble that's going to cause. And my healthy skepticism is, if we can avoid it as much as possible, then great. And if we do have to do it, let's use more like message passing style than locking and threading. And then I've kind of essentially outsourced the correctness of my thread library to something which is a single producer, single consumer queue, or a multi. And then hey, the best kind of shared state is the one that you don't share with anyone at all. Mutable shared state is like the one you copy and give to someone else, and then it's not shared.
Yeah. Yeah.
But this was not meant to be about threading.
No, well, I mean, it is kind of tangentially. So I'm trying to think of other situations. So this has got my brain going, of course, about are there other things that I have sort of leaned on my tests to do for me that I haven't really thought about before, because it's sort of just it's just sort of never come up, right?
Yep.
And if performance optimization is refactoring, and sort of thread correctness or sort of scalability or that sort of dimension of code changing is also refactoring.
Yep.
Then what other dimensions of code change do we have in the various systems that we work on, where the tests should not change as a result of you doing it, right? Obviously, there's the most fundamental one, which is sort of removing complexity and changing things.
Yep.
Another one might be, and I think this is maybe a little bit more controversial.
Oh.
But another one might be, or controversial in the sense of I'm going to say this and I'm not sure that I actually agree with it 100% of the time, but maybe. I'm exploring some ideas here, right? But maybe one dimension of this is sort of dependency and platform upgrades, right? So one of the things that I expect to be able to do, for example, is working on a Java project, upgrade the version of the JDK, rerun all of my tests, and if any of those tests fail, I know that upgrade has caused a problem, right?
Mm-hmm.
I don't know that it necessarily follows, but maybe, that if I were to do that and all the tests pass, that I know that the upgrade is okay.
Right. So that's really interesting, because this is something I do a reasonable amount. Our system has some kind of essentially major version number, which is here's just a suite of packages that we've solved. They all work together, and from time to time we have to upgrade that. It's essentially the equivalent of upgrading your Linux distribution from Ubuntu 20 to Ubuntu 22 or whatever, but we do it far more often. And I typically bump that number in my code and then type make test and watch it sit there and pull down all the new packages that come with the latest version, build against them, and then all the tests run. And if everything passes, then I just assume that everything's fine with that, right? But the thing is, I have never written my tests to test the assumptions in third-party packages.
Right.
I assume that they are right. So if it compiles at all, well, that's probably most of the battle won in my case. If the tests will pass, then one of two things may be true. One, I exercise some functionality, and the part that I exercise, maybe not even on purpose, but it does at least do the same thing, or at least enough of the thing that I care about that my test passed. Or two, I didn't care about that functionality enough to test it directly because I have a fake or a mock or a whatever in front of it. So I'm not actually going off to Amazon and checking that the S3 library still works. I have my own fake S3 thing, and everything's phrased in terms of that. So I will never find out that it broke until I go to production. So, and I mean, I've seen people talk about writing, if you depend on behavior, you should write a test for external behavior. And I'm sort of sympathetic to it, but I don't have enough hours in my day to test other people's code. I kind of just assume it all works, which is actually, now I say it out loud, horrifyingly naive.
I know, and I think this is the problem that I have with this, and this is why I think this is controversial, because I use basically the exact same approach, right? I'm not writing tests for the dependencies that I have, but I also don't have a better process than upgrading some dependency or the standard library or whatever, running make test, maybe like deploying to the test environment and starting the system up and be
poking
like,
it with a stick a bit. Yeah, exactly.
Right.
Yeah. Well, I mean, I do this once a week. Every Monday night, I upgrade all of the Compiler Explorer's dependencies and I run all the tests again, and then I deploy to our staging instance, and I literally do that. I poke around, I do a few compiles, I have my little list of things I do, and then I go, I guess that works then, and then
yeah.
Sometimes it hasn't. Someone goes, "Oh yeah, this syntax highlighting isn't working anymore." I'm like, "Oh shucks, I don't have the bandwidth to write full UI tests for third-party components, for example." And so sometimes things break.
Right. So it's like that. I don't think that I can justifiably call that kind of change refactoring, because I have no expectations that problems would be caught. I don't know. I just don't know how to think about it. But
I see what you mean. So you started this by sort of positing that what other things have the smell of refactoring, even if we couldn't call them refactoring, where we are leaning into the test as like, well, this is my function to determine whether or not this was successful, that the other thing that I did was successful, measured by an objective intersubjective metric of the tests. So yeah, I mentioned moving things around for compilation, which is a bit like just more traditional refactoring. I wonder, does I think no. Again, a lot of these other things are just code changes that have a more of the sense of genuine refactoring. But it called to mind when I took my largely C multi-user dungeon code from like the 1990s and was slowly, like line by line, turning it into C++ with all the trimmings. I didn't really have that many automated tests. We had a few, and I wrote a few. And in a way you could argue that is reducing complexity, although you could also argue in quite a very real way I was introducing complexity by turning it from like 90s era C into template C++, but it felt like it was a useful thing to have, and a useful thing to be able to do was to be able to run those tests and say like, hey, I've no more am I manually allocating and freeing all of these pieces of memory now standard strings, the C++ runtime is doing this all for me, and it all still works. All of the string manipulation stuff still work. Again, it's more like a traditional feel, but it's like a language upgrade is what I suppose that would fall under. Hey, I'm moving from JavaScript to TypeScript, and most of my tests are still written in JavaScript, and now they all still pass. Okay, that's cool. I can be reasonably sure that I haven't broken anything just by renaming the files and running them through a processor. What else could there be? I mean, you've mentioned operating system kind of upgrades. That's another thing.
Yeah. I suppose if you were doing anything with sort of like generated code and you changed the way that you did the code generation, that would be another kind of thing where you would expect your tests to continue to pass, and it's very possible that they would catch some problems. I think it's not quite as unjustifiable confidence as I upgraded the libraries and all my tests pass, because we explicitly don't. Right, we explicitly don't test that behavior, because it's sort of like, okay, well, where would you stop testing that behavior, right? Do you trust the CPU? Do you trust the electrons, right? Like, you got to draw the line somewhere. But with this sort of code generation, there might be some situations where you say, we do actually at least sort of transitively can say, if this code generation is broken, something upstream of it is almost certainly going to break, right? So you could rely on the tests in that way.
It's an interesting point you bring up. Where do you draw the line? I was actually having a discussion this morning with a friend over this kind of thing, and this is a complete subject change. Well, maybe we can bring it back round. But I was sort of saying that pragmatically, all of us have like a ceiling and a floor of our knowledge. As high level as you're prepared to go. Like, I fall down at some of the more complicated type theory in the world, but I'm sure there are really clever things that can, and higher level functional stuff is above me and I can't get. And then there's a floor below you by which you kind of go, I assume I have some knowledge of this level. I'm confident to here, and I know that there's a couple of floors down, and I assume that anything below my understanding is just works, right? And so that might be the API you're calling. It might be the operating system you're running on. It might be the CPU. It might be the physics of the like some level that you've got a flaw, and I think we have to, as humans, you could always get, you say, oh my God, is there a bug in the compiler? It's like, well, probably not. Probably there isn't a bug in the compiler. Every now and then it is, but otherwise you have to hold it
right
in order to keep the abstractions in your head, or the sort of like the boundaries in your head finite. It's sensible to have some simplifications where you go, I just assume this is right. And I think, operating systems we tend to believe in. Third-party APIs, which is the thing I'm most shaky on, again, now saying this out loud, like the random GitHub repositories we're pulling from. But you still tend to assume that they're right. I mean, maybe you treat them a little bit more hostilely, something like that. Like it's not... it's not beyond believability that you'll find a bug in a third-party piece of software, and that's what GitHub is great for. You go and file an issue, you ask on a Discord or whatever. But if you were writing tests, where would you stop?
Right. Yeah. I mean, the analogy that I use for this is I feel like there was some physics professor who was many decades ago who was doing research into quantum physics and then started like walking around with like risers on the soles of his feet because he was scared that he was going to fall through the floor. Right. And it's like, and you just sort of do the math and you're like, wait a second, this is possible. And it's sort of like, you can't live your life worried that all of the electrons in the ground beneath you are going to suddenly align in such a way that your legs just sort of pass through the floor. And that's just how it's going to happen. Right. Like maybe there's some infinitesimal probability of that, but you just can't do that. You have to have, I did a talk that was sort of adjacent to this once, which is like sort of tongue in cheek saying all engineering is based on faith.
It is, right?
Faith-based engineering. And it's sort of like at a certain point, you just have to have faith that the CPU is going to be able to add 1 and 1 and get 2. Because if you do everything constantly questioning all of the abstractions beneath you, you won't get anything done, right? I think what makes a senior software engineer a senior engineer is that they've developed a sense for when that can be trusted. Yep, I think if I add 1 and 1, I'm going to get 2. And when it can't be trusted, where it's sort of like, what do you mean I can't treat this TCP socket like a file, right? Because, you just got to learn all those situations in which the abstractions are there, and
that's
sometimes
a really
they're
fascinating
reliable, and sometimes they're maybe not quite so reliable.
That's
right?
part of what factors into the seniority of someone, is like understanding when to draw the line, and also when there's just enough of a whiff the other side of the abstraction that you're like, I'm actually going to single step into this third-party library, and I'm going to have a look through it because I now smell a rat. I think there's something going on here that I don't understand. Maybe there is a bug in it, or sometimes I have to crack out the Linux source code and go, oh, that doesn't look right. Oh, this is a bug, right? It doesn't happen very often, but it happened and it will happen. But knowing when to stop, and also this is when I look for folks to employ. One of the things I like to look for is the sort of tenacity of like knowing, being able to follow that thread all the way down if you need to. If you hold your breath, big deep breath, down you go through the levels all the way to the very, very, very bottom, and then maybe you come out and you've learned something, and then you come back up for air, and then hopefully you don't ever have to go beneath that level for again, or for at least for a very long while. And that's a really important thing to be able to do. But then similarly, being able to say, I'm not even going to go down beneath my floor right now. I've got a very well-defined floor of where we think the problems are buried, and we don't need to go beneath that, because otherwise, as you say, you'd never get anything done.
You're right. You're going to fall down a rabbit hole and never come back, right? And I think this is directly related to kind of what we were talking about in terms of being able to draw this line and have these dimensions of refactoring that is beyond just redesigning, because again, this ties directly into the problem of overspecifying in tests, right? Or underspecifying, right? If you go the other way, right? If you're mistrustful of abstractions that are beneath you that you should be trustful of, or it maybe makes sense to it doesn't make economic time sense to distrust them, then you're going to overspecify in your tests. And that has many problems, one of which is you're wasting time writing tests for things that are probably not going to break, but also you're limiting the dimensions of refactorability that you will have in the future because of an unwarranted fear, right? And also on the other side, right? Like you don't test things enough because, maybe we should have some situations, you and I, where we write some tests specifically for when we do that next upgrade.
Yeah.
Just to make sure that this thing really still works the way that it should.
Well, those things get informed a little bit by experience there. When you've been bitten a couple of times by stupid whatever file handling in library Bob,
Yes.
you go, well, I tell you what, while I was even trying to work out that this was a problem, I wrote some tests just to sort of pave the way or to explore the space, and I tarted them up a little bit, and then we checked them in because they didn't hurt us any, and they might just solve at the next one. But that always has a sense of a feel of like bolting the stable door after the horse is bolted, like whatever I forget, shutting.
But I mean, I think it makes sense to sort of wait to feel some pain on those fronts, because if you did that speculatively, where's the boundary? You'd be testing everything, right? So but that's, I think what this is, getting that level of specification right in the Goldilocks zone where not too much and not too little takes experience. It takes, some hard fought experience sometimes, but when you get it right, or when you get it close, you're able to do all of these things. You're able to optimize your code with a set of running tests to tell you that it's not broken. You're able to, change your threading model, again, with tests that tell you that it's not broken, right? You're able to do all of these other things that we can use our tests for. But if you either overspecify or underspecify, your ability to do that will be greatly limited.
Yeah, that's awesome. And you've somehow managed to tie my complete tangent back round to the original topic. So yeah.
Well, it turns out these things are usually related. It's like there's subtle or sometimes not so subtle dependencies on these things, and you can see them. They're there.
Well, fantastic. I think that's a great place to pause and
call it for today.
Go refactor some code, or go back to my compilation
optimize.
speed. Yeah, or optimize it. Yeah.
Yes.
I mean,
right.
Go optimize some code. That's always a fun thing to do. You've been listening to Two's Complement, a programming podcast by Ben Rady and Matt Godbolt. Find the show transcript and notes at www.twoscomplement.org. Contact us on Mastodon. We are at twoscomplement@hachyderm.io. Our theme music is by Inverse Phase. Find out more at inversephase.com.